Am I audible? Excuse me, can you tell? Am I audible? Okay. Okay. Can you see the screen which I have shared through OneNote? Can you see the screen? Anybody please unmute yourself and tell.
Yes, sir.
Okay, thank you. Okay, so before starting, let me introduce myself. My name is Shovik, and right now I'm doing a research at IIT Madras under a Pradesh Counseling. Uh, this is the second live session for this Algebra 1 course. Okay. The main purpose of this course is to solve problems and also clear doubts in problems and also make some difficult concept. We shall try to clear some difficult concept. Okay. So, before starting, let me know how many of you are from different background. You can raise your hand in the Google Meet. How many of you are from different background? Please raise your hand. Okay, so all of you are from mathematics. I'm assuming it. Okay. Also, do note one thing that I have shared a Google Form link through the chat. Okay. Please submit the Google Form in order to register the attendance. So, okay, so after permutation group, I have seen the started the group definition axioms and order conjugates some basic things. Okay, so okay, so I think I need to do basic problem from basic group theory, but first let me know what you want. So any suggestion that what should I do? I mean, I know. I mean, if you have any suggestion, then I will do that. Then I think that will be very much helpful for you. Please unmute yourself and let me know. Anybody, please.
So can we do Chinese reminder theory?
Yeah, sure, sure. Yeah, sure. And what about others? Yeah, yes. One thing is the Chinese remainder theorem. This Chinese remainder theorem can be done, but actually, there is a ring theory version of Chinese remainder theorem, but since a group theory course, so okay, we'll see that. And except that, I mean, I'm asking it regarding the group theory things.
Okay, sir. Okay.
Okay, and also let me know how many of you know the definition of order of an element. What does it mean by conjugacy of an element? How many of you? Or anybody, please unmute yourself and let me know what does it mean by order of an element. Anybody, please let me know the order of an element. What does it mean?
So the minimum number,
Yeah.
minimum positive integer r,
Mhm.
such that some particular element belonging to
Right.
be a base to that power, it should be
Mhm.
identical.
Yes, right. Okay. And what does it mean by two elements A and B are conjugate? What is the definition of conjugacy?
So for two elements belonging to
Mm,
group G,
mm.
G and G dash is conjugate to G if there exists an element U belonging to the group such that G dash is equal to U G inverse.
Right. Okay. Good. Uh, since okay, so also let me know how many of you has solved some problems of basic group theory, or how many of you has no how many of you have no idea in in the group theory? No idea. Please raise your hand so that I can show the problems. Okay, so since okay, so let's start some groups. Okay, so okay, take an example of 11. So, okay, so some of you just asked me to put order again. So um, so do you know the group Zn? Do you know this? You can reply in chat also. Do you know the group Zn? Z suffix n.
Yes, sir.
Okay. So consider the element plus one in Zn. Okay. Now the order of the elements in Zn are class 0, class 1, class 2, dot 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 class n. Okay. So for sake of simplicity, take the element, take consider Z3 and now consider element 1. Okay. Now observe that 1 plus 1 by definition is class 2 and class 2 plus 1 is by definition class 3, but it is nothing but same as class 0. So this tells that order of this element class 1 is equal to 3. That is, if I add this element class 1 3 times, we will get the 0 in Z3. So this is an example. Okay. One more example will be like, okay, let me think. Yeah. For example, consider again Z3 and consider the element class 2. Okay. Now, if I add class 2 two times, this will give class 4. And this is nothing but class 1. And if we again add class 1 with class 2, this gives class 3, which is nothing but 0. So order of this element class 2 is equal to 3. So these are some kind of examples following the, I mean, which, so in order to calculate the order, you need to somehow need to manage that at least how many times we need to add that number to get the identity element. So that's the way of calculating the order of an element. Okay. So, um, and some more examples like yeah. So you have so do you know the group Q3 quaternion group? Yeah, Nivedita, please tell. Yes, you have raised your hand. Tell. Yeah, those who have raised your hand, please tell.
It's a group of order 8 in which uh, every element uh, means the
Yes,
order
right.
of elements are 1, 2 and 1 and 2 only. 1 is the only element of order 1 and every other element is of order 2.
Right, but you have said some information about the
Okay,
order of
sorry.
yeah, this yeah. The thing is, order of one is one obviously, and order of minus one is two, and order of other elements are four. I mean, actually, it is defined in the way that I square equal to minus one, right? So that's why order of I is four, right? So that's why. So in this quaternion group Q8, order of minus one is two, as Nivedita or yeah, some people order of I should here it is four because I mean if we consider I square, it is minus one, I cube minus I four minus I square, so it is one. So that is the order of I equal four. Similarly, order of J, order of K, both equal to four. Yeah, these are some examples. So yeah, so yeah, so yeah, these are the basic examples of calculating the order. So Lavarna, does this resolve your query, or do you need some more examples? Okay. And
Sir, can you explain the dihedral groups?
yes, I will.
In which like I have a particular problem how they defined the relation that they said it is generated by two elements take a rotation and the horizontal flip, then there is a
Yes, yes,
relation between them. So
yes,
how that
right.
relation came? Like
Yes, yes. So, dihedral group. So we start with the simplest example, D8. Okay, because it is easy to visualize. Okay. So, dihedral group consists of two things. One is rotation, and another is reflection. I will explain what the by here we which axis we are taking. I'll explain. So it comes as follows actually. So choose the unit square. Sorry, take the unit square. Okay. So in a unit square, there are four possible rotations possible, right? I mean, this is uh, I mean all the 90-degree rotation anti-clockwise. These are the four possible situations: A, B. Rotation. I mean, here it goes here. And another rotation will be again 90 degree anti-clockwise. Again 90 degree anti-clockwise. Okay. These are the four rotations. Okay. And rotations are denoted by R. And another is reflection. Reflection comes as follows. That is, take this unit square and keep it on horizontal surface and consider this z-axis. Okay. And then we are I made a small mistake. This will take small second. The reflection comes as follows. This is the axis of reflection. If we take it A, B, C, D. So by doing reflection with respect to this axis, so we'll get this A, B, B, C. Okay. So this is the reflection, and there and above we get the four rotation. Okay, and these reflections are denoted by S. Okay. Now the thing is, you can observe that SR, sorry, yeah. So the thing is, the D8 is basically the group generated by these rotations and reflections, such that rotations means if we take the if we do the 4-time rotation, we will get the same position. So that's why R to the power 4 is equal to 1. And reflection, if we do the same reflection 2 times, then we will get the same position. So S square equal to 1. And also there is one relation which is RS is equal to SR inverse. Okay. And now how it comes, the thing is, RS means what? First reflect and then rotate anti-clockwise 90 degree, and SR mean RS, I mean S compose R inverse in right side, means first you rotate the square clockwise 90 degree, then take the reflection. You can easily, I mean you can clearly check, you can check it right now that it will give the same position actually. So that's why we have the relation RS equal to SR inverse. Okay, you understand the point? I mean, you can look at it, think it is a map R compose S equal to S compose R inverse. S and R is the rotations or reflections and acting on the unit square. Okay. Then you can check that both gives the same position actually. So that's why we have that relation. Okay.
So do we need to specify that in like in
Yes.
three-dimensional, the dimension of space, do we need to mention it? Because it's a set of all rotations you are taking and reflection you are taking. So reflection, to take reflection, we need uh, we need the z dimension, z direction, right, through which we are rotating.
Yes, yes.
When we so another dimension we are using, like the third dimension we are allowing so that we can flip it.
Yes, right, correct.
So it's
you
not
can,
set of all rigid motions.
yeah, it
It's a
is
set
not
of
set. It is not the set of all. I mean, we have fixed some axis, fixed some position. Then we are doing all the things. It is not all possible. Okay.
uh, if we are if we allow only dimensional space, then the only rotations are the only
Uh,
elements.
I am not sure about that actually.
Because if we are not, because if we are not allowing the z dimension, then we cannot flip it, right?
Right.
So in two-dimensional only 4 elements are there. In 3 dimension there are 8 elements, all
Yes.
symmetries.
Right.
So
Right.
do we need to specify the D8 has in 3 dimension only? Because
No,
if
no,
we
you
allow
can.
one more dimension, we don't know what are set of pulse matrix.
Yes, yes. The thing is, geometrically, at least as per I know, geometrically, when we are considering D8 geometrically on 3 dimensional, maybe in higher dimension there are some things, but in group theory does not deal with that actually. So I don't have a knowledge of that thing. But as long as you are writing D8, D4, or D16, whatever, everything is happening in 3 dimension. Okay.
Okay, sir. And sir,
I
when
mean,
we
for example,
write
here,
D8 in this set form, so
yes,
set form that it is generated by two elements R and S with these
yes,
relations.
yes,
So if I write only two relations like R to the power 4 and S to the power S
yes,
square is identity, and
yes, yes.
third relation if I don't write, then the
Hmm.
set will consist more elements, but that's not a problem, right? Even write the third relation, it automatically
Yes, yes,
satisfies.
yes, yes. You are right. I mean, it will again
So
be a
means a set.
it will again be a set and satisfy same relation. I mean, it will be a group, but it will be a bigger group. That's it.
So then my question is that if it is already satisfied by the first property, first r power 4 to equal to 1 and r square s square is equal to 1, it
Yes,
already satisfied the third statement, that is rs is equal to s r inverse. Then what is the
yes,
need to write here, mention here rs is equal to s dot r inverse?
yes, yes. Okay. So the thing is, so here we have the geometry description, and from there we have some relation automatically rs equal to sr inverse, right? It comes automatically. Okay. But when it comes to algebra, we are directly writing some r s, some r to the power 4 equal to 1, s square equal to 1. I mean, this r and s has nothing to do with this reflection rotation. Okay. I mean, from algebra perspective, we need to give the relation rs equal to SI inverse, because here r and s are some abstract element. We don't know whether it corresponds to square or correspond to something or not. Okay, these are some abstract things. That's why we are giving this relation here. Okay, I mean, when automatic lump, that is okay, but when you are directly writing d8, then we need to mention r comma s with some relations. That's why, because when you are
Okay.
solving
Yes. Thank you.
problems, you will not remember that the geometry description of d8. You will only remember the algebra description of d8. That's why we always need this. Okay, abstractly. Understand?
Okay, sir. Thank you.
Yeah.
Yeah. And sir, how do we know that there are no more relations? Like these are the only relations that can define this group.
Yeah. Okay. So so for example, you have rs equal to SR inverse, right? Okay. So for example, you now want to calculate rs square. I mean, you may wish to calculate this, right? Now, if you have this rs equal to SR inverse, so rs square equal to rs into s, right? Now rs equal to, we know, s r inverse into s into r inverse s, right? Now this can be as s of r cube s. I mean, you can calculate it that it will be actually s r to the power minus 2. You can calculate using this relation. Okay. The thing is, relation gives what? Relation gives it. I mean, why we need the relation? Firstly, okay. The thing is, if r is equal to sr, then it will be abelian group, right? But this is not the case. So we need to know all possible r to the power s to the power j is what. But the thing is that the way in which the r to the power 4 equal to 1 and s square equal to 1, it gives, and together with rs equal to SI inverse, gives all possible r to the power I into s to the power j equal to s to the power j to r to the power minus I. You can calculate it actually by using this only relation. Okay. So that's why we only need one relation. Okay. That's it. I mean, we may need more relation, But since there are only two generators and they are not commuting, so they are not commuting. That's why we need what is RS and what is SR, and we RS is some RS equal to S of R inverse, and then this gives all possible value of R to the power I, S to the power j in opposite direction. So that's why only one relation is sufficient. Okay, but
So
in yeah, yeah. Hello?
in our mind, like what d8 is the set of all rotations and the this rigid motions. To describe that, that is the algebraic expression of that. But if we allow if we restrict it, means like if we allow more relations, then the resultant structure, is it a subgroup of that? If I like the more relations I give the constraint in the group, like the smaller element will remain,
Yes,
right?
yes. Right, right.
So
Yes, yes.
will there be a subgroup of
Yes,
the
yes. It
given?
will be a subgroup because it is already satisfying those relations, right? So it will be a subgroup.
So every subgroup we can write along with these three relations some more relations.
Yes, right, right.
Okay.
Yeah.
Hello, sir.
Sir, you're muted, sir. Uh,
No. Please. Am I audible?
Yes, sir.
Okay. Sorry, somehow my headphone is not working actually. That's why. So, are you able to see the screen?
Hello?
Yes, yes. Are you able to see the screen?
Yes, sir.
Yeah.
Sir, I have one more question.
Yes, yes. Yes, can.
So, sir, we say every group is isomorphic to a subgroup of a group of permutation.
Yes. Okay.
Permutation group.
Hmm.
So, is any subgroup is of the form Dn? Like Dn means like if I take any subgroup of Sn, can it be written is in the form of Dn?
Okay.
Like dihedral group. The only thing is I'm increasing, like I'm allowing more dimensions. Means when means four dimensional rotation, or I want to know what does it mean like to allow more dimension means what? Means the allowing the z direction gives us freedom to flip. The allowing
Yes.
2 dimension gives us freedom to rotate. So
Yes.
what is the allowing the 4 dimension means what? And if whatever it means, does it say that any subgroup of Sn can be isomorphic to rigid motions, like a group of symmetries?
I don't have that much knowledge about the fourth dimension because book theory does not deal you directly with that. Okay, so I don't. That's why I don't know the actual answer. Sorry.
Actually, sir, I read somewhere that it is set of all symmetries. So that's what I don't understand. What is mean by set of all symmetries?
Okay, I will clear this doubt by next live session next week. Okay, I will I will read it by myself. Then I will then only I can tell you. Okay.
Thank you, sir. Thank you.
Can anybody has any doubts? Or should we start off doing some problems? Anybody any doubt or should we start doing some doing problems? Please let me know.
Sir, could you please explain, like in very elementary terms, group actions?
Sorry, can you please be louder?
Uh, Group actions, sir.
So,
Like
yeah, okay, yes, yes.
definition and basic.
Yes, yes, sure. So you can see the screen.
Yes, sir.
Okay.
Yes, yes.
So group action, I am studying for the definition. Okay.
Okay, sir.
Okay. Yeah. So by group action we mean uh, there will be a group G and there will be a set. Normal, it's a just set. Okay. And we say that G, this group G, acting on the set capital X if there exists a map, we define it psi from G cross X to X such that psi of E dot X is equal to X and psi of G1 of psi of G2X is equal to G1, G2. And if such a thing holds, then we say that the group G acting on this capital X via this map psi. Okay, this is a definition of group action. For example, consider Z acting on R. I mean, consider this map n comma x goes to n plus x. It is a group action because you can easily check this property. Sorry, this property 1 and property 2 holds true for this example. Okay, this is a group action. Similarly, consider the following example that like multiplication. Like suppose mu n is equal to although z belongs to C such that z to the power n is equal to 1. Then this group mu n acts on C as follows. Xi comma z goes to xi. So here's a group action. These are the examples. Similarly, 0 comma 1 plus s1 to s1 t1 comma e to the power 2 pi it goes to e to the power 2 pi I t plus t1. It is a group action. It's action. And I mean, simply it is action. That's it. So these are some definitions and examples. Okay.
Okay, sir. Sir, in the definition,
Yeah.
definition of group action, it is that psi function from G cross X. Is it a direct product?
Sorry. Wait. G cross X. Wait. Is it G?
Okay.
Sorry.
So that is not a direct product.
Yeah, it is just Cartesian product.
Okay.
Now, one interesting happens is that if G, this is a way of writing x on x, and where I mean, this notation means G acts on x via this psi. Then, for each G in G, is equals to psi gx will be bijection. So it is a fact and it can be directly proved by the definition of group action. So how to prove this? You need to check that this tau g is a bijection for each. Okay. So how to check injectivity? Suppose tau gx1 is equal to tau gx2. Okay. This implies what? Psi gx1 is equal to psi gx2. Now do this thing. This implies psi of e comma x 1 is equal to psi of e comma x2. And this implies x1 equal to x2. So this is injective. I mean, so tau g is injective. Understood?
Yes.
And what about surjectivity? So take a x belongs to x. Now observe that psi of g of psi of g inverse comma x. This is nothing but psi of e comma x is equal to x. So that is tau g of psi of g inverse x is equal to x. That is tau g is also surjective map. So that's why for each fixed g, this map x goes to x in obvious way. It will be the bijection map. I mean, will be bijection. Sorry.
Sir, could you please show the part where surjectivity is proved?
Yes. Yeah, you can see, right?
Okay. Yes, yes.
Yeah. Someone already. And yeah. Now comes to the group theory thing. I mean, some group actions which usually offers with the group theory. So first example will be like G cross G to G conjugation. G X goes to G X G. It is known as the conjugation action. Then there is another type of use famous group action. Suppose G is a group and suppose the H is a group of G, okay? And LH, by LH we mean the set of all left cosets of H in G. Then there is an action G cross LH to LH, G comma XH goes to GXH. So it is known as the left coset action. Sorry, it is known as actually coset action. Okay. And there is another action name which is known as translation. G comma X goes to GX. Especially this is known as the left translation. So these are the some examples and some definitions. Okay.
Okay.
Now, hold on. Wait for 2 minutes. Let me come with my notes. Okay. Wait for 2 minutes. Now, you have what is the name? So you know that the theorem about the fact that any group of order n can be embedded inside Sn, right? So how you have proved this? Which proofs you have seen? Yeah, anybody? So you have seen the Kelly's theorem, right? Which says that any group order can be embedded inside Sn. So can anybody please tell? I mean, what is the proof? I mean, or have you seen the proof? And if yes, then which way it has been proved there? Anybody? Anybody? Okay. So, I mean, there are many ways to prove the Kelly's theorem that any group order can be embedded inside SN, but directly using group action, it can be proved. So, let's see how we can prove it using the group action. Okay. So, we have said if we wish to prove this using group action. So, what is the action we will take? Take the left action. The left action. Okay. Ex goes to Gx. Then we know that for each G belongs to G, the map tau G from G to G, X goes to Gx, it's a bijection, right? And also we know that order of G is equal to N. So now consider the set AG. AG means the set of all bijections from G to G. Now also since each tau G is a bijection, so we got a mapped row from G to AG as follows. G goes to tau G, right? Now we claim that, okay, so before this, since we have order G is equal to N, so AG, that is a set of bijections from G to G, is isomorphic with Sn. So now if we claim, and I mean if we can show that this row is injective, then this tells G can be embedded inside Sn, right? So check that row is injective. I mean, I am waiting for some minutes. Please check that row map is injective, and which gives the Kelly's theorem. Okay, please check it. That row is injectable. Please check that row is injective map. So let me check the how to show the injective. So suppose E1 is equal to activity, right? So we will check what. Suppose rho G is equal to tau E, the identity. This implies what? Tau G is equal to tau E. This implies tau Gx is equal to x. This implies Gx is equal to S for all x belongs to G. This implies G is equal to identity by taking x equal to identity. So this tells that rho is injective. This shows that this group G can be embedded inside S. Okay. The Kelly's theorem. Does anybody have any confusion or doubt till now? Anybody have confusion doubt till now?
Sir, could you please explain the proof again?
Uh, Explain what? Sorry.
The proof, sir, proof of this.
Yes, yes. So basically,
Continue.
yeah. So basically, we are trying to show here that any group can be embedded inside Sn if the group is of order n. Okay. So for this, we are here using the tools of group action. So for this, we need to choose the action first. So we take the right action. Right? Yeah. Sorry, we choose the left action. Choose the left action here. That is gx goes to g dot x. Okay. And since there is an action, so we know that for each fixed g, we will have bijections tau g from g to g. So this gives a map rho from g to ag, where ag is the set of our bijections from g to g. Okay. Now observe one thing, that since order of g is equal to n, so ag is isomorphic to Sn, right?
Yes, yes.
And the map is g goes to the map tau g. And I mean, yeah, here actually I should tell that rho is a group homomorphism.
Order of G should be n factorial.
Any group of order n can be embedded inside S. Group should be of order n. Okay, not factorial. I mean, sorry, what you have said, order of G or order of AG? I mean, if order of G is equal to n, then order of AG will be n factorial and it will isomorphic to Sn. Okay, and now we are trying to show that rho is an injective map, because if we can show rho is an injective map, then G is embedded inside AG and AG is isomorphic to Sn. So rho, injectivity of rho tells that G can be embedded inside Sn, and the following calculation tells that rho is an actually injective group homomorphism. So yeah, that's all. Right? Everyone understand?
So, what is the difference between left action and right?
Yeah, firstly from the definition there is a difference. Okay, the thing is, what is the definition once again? Yeah. So for the right action, I mean, here group action, I mean, here we are writing that G acting on X, right? It is actually a left action, because if you look at the map psi, then G acts from the left on X. Okay. But for the right action, psi will look like this. I mean, the obvious things, right? Like,
By some example, can you explain?
yes. Example means, okay. Example, yeah. For example,
Example, I mean like some right action which is not left action means
no, no,
kind of. If you can give any.
right now, no, no, right now it isn't possible, because till now we don't have. I mean, till now, sir did not develop that much tool to give that example actually. Okay, but there are some actions which is right actions but not left actions. Okay, and if some of you know, read the subject algebra topology, then there we will come to some right actions which is not the left action. But right now we don't have that setup to give examples actually.
Actually, sir, still the definition looks similar. Can you explain again?
Yes,
Like,
yes,
what is the difference?
yes, yes, definition is similar. It is right. Definition is absolutely similar. In reality, there is no difference, but the, I mean, one second. Yeah, there is no difference, but the, what does it mean by left action is a right action? Means suppose G is a group and we have some map psi 1, and suppose this psi 2. I mean, if you want to get this psi 2 from psi 1, then possibly sine has to be psi of x comma g is equal to psi 1 of g comma x. Okay, I mean that's the definition. Okay, I mean it is obvious way. Okay, but there are some occasions where there are some occasions where there are advantages of choosing right action over the left action or the vice versa. Okay, so that depends on the particular situation, but essentially by definition they are same, but they have used in some different context. That's all. Okay.
So in this course, are we using like the distance or
No, no.
like same action, so we don't have to worry about it?
In this course, we no need to worry about right or left. Action means g cross x to x. That's it.
Okay, thank you.
So yeah, so this is the Kelly's theorem that g can be embedded inside a string. Now, so yeah, once again. Okay, so using this, prove the following. Okay, so let's better to do some problems also, so that any finite group using Kelly's theorem, put the any finite group is isomorphic to a subgroup of an. For some n, I mean here this n is not the order of the group. Okay, any group can be embedded inside n for some n. Okay, using the Kelly theorem, try to prove it.
So here the group is
Yeah, sorry.
what is the group name?
An is the set of all even permutations. What about others? I mean, don't you? I mean, all of you don't know about the group N. N is the set of even permutations that is that elements. So, do you know about even permutation? Do you know about even permutation? The even permutation. Okay, so so actually it will change the context also. Okay, so so we will leave. Okay, so leave this question because some of you might not know about the group A. Yeah, okay, that's the basic introduction of the group action. Yeah, that's the basic thing, the group action. But there are some more things which we see in the third or fourth lab session, but not today. Okay. So, yeah, do you wish to discuss some theoretical part, or is it okay to go with problems? What do you want? I mean, should I go to problem with problems, or if you wish to suggest some theoretical part, we can also discuss that.
Problem, sir.
Studying the problem, let me know. Do you know about this theorem?
Sir, the last question that you gave, uh, means does it mean that every symmetric group of order n is isomorphic to some am, or
Yes, yes, yes.
some
I mean,
subgroup of am? That is what you are saying?
no, 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 it is not only symmetric group. Any finite group. Yes, I mean obviously symmetric
Yes, sir.
groups.
In particular, SM.
Symmetric groups they are right. Yeah, symmetric
Uh,
groups they are right. So any symmetry can be embedded inside. Yeah.
but n greater than equal to 4, the only subgroups of an are uh, only an and the 0 itself, right?
No, no, no. It is not only sub. It is the only normal sub. Okay.
Okay, okay, okay. I'm sorry.
I mean, yeah, it is only normal sub. Right. Okay. So is that suppose I mean it's a fact or a theorem or problem whatever. Suppose G is a group and suppose A be an element of G and suppose order of A is equal to n. Now if A to the power m is equal to identity, this implies n to n. Do you know this theorem or this thing?
Yes, yes.
And secondly, order of A to the power t is equal to order of A by GCD of order of A, comma. Do you know this?
Yes, yes.
So, yeah, please solve these two problems. Calculate the order of the element 6 sorry, in Z14. Sorry. In Z14, calculate the order of the element.
Sir, order of elements it's in Z4.
No, no. Sorry, can you please repeat?
We should calculate the order of elements it's in that group. Sir. What is it?
Oh, Z14, 14. Sorry.
Okay.
You can directly do it, or since you can use this theorem also. Okay, I mean this fact also.
Sir, it's 7.
Yeah, right, correct. How you have calculated? By using a formula, right? How you have calculated by using a formula, right?
Yes, yes.
Okay. Now, following problem. Let G be a group and order of G is equal to E. Show that there exists. So G is a group of even order. You need to check that there will exist at least one non-identity element A such that A square is equal to identity. Think in easy way. That's the only hint way I can give. Okay. I mean, this problem is really based on counting. So think it its own way. I mean, observe that this A square equal to E is same as writing A equal to A equal to A inverse. Okay. Now think some direction regarding counting.
Sir, we can pair up the elements in such a way that
Sorry.
sir, we can pair up the elements in such
Yes,
a way
correct.
that A is equal to A inverse.
Yes, correct. So can you please tell the full argument for others too?
Sorry, sir.
Can you please tell the full argument for others also?
Sir, can I just walk out a bit and sir?
Sorry, I didn't get you. Can you please repeat?
Should we just walk out a bit and say?
Yeah, no, that's okay, but you can just speak, right?
sir. Yes, sir.
Yeah, yeah.
If there is no unknown identity element, then order of group is 1.
No, no. Okay. So as some of you tried and they solved it. Okay. So thing is, if I mean, so consider this set G and P are all those element P are all those element who which is not equal to the inverses, right? So these are two. I mean, they are pairing. So we will get two times of something plus an identity element, and assuming the fact then that there is no element who's equal to its inverse, so this is some odd number, so that's why we must have one element which is equals to its inverse. So that's the argument. So everyone understand the argument? Consider this problem. PB group and A, B in G such that AB is equal to P and order of A, order of B are relative. Show that order of AB is equal to order of A multiplied by order of. How we can prove this? I mean, yeah, G is the group and with AB equal to BA and also given order of A and order of B are relatively prime. Then we will check the order of AB is equal to order of A multiplied. Sorry, I mean it's just a multiplication order of A into order of B. Okay. So yeah. So how we can solve this?
So first we can let the order of A is equal to n,
Yes.
and the order of A is equal to n. So A power n is equal to, no, sorry, A power n is equal to E, and A power n is equal to E.
Yes, right.
So we can, so identity is equal to identity into identity, so it's equal to A power n into B power n.
Then think about it. So try for some minutes. Then I will tell you if you get out. Okay. Try for some minutes first.
Sir,
Yeah.
am I audible?
Yes, yes, please.
Sir, order of A must divide order of AB. Similarly, order of B must divide order of AB. So order of AB is the smallest positive integer. Both order of A and order of B divides. And
Yes.
the order of A, LCM of, sorry, GCD of order of A and order of B is 1 implies order of AB is order of A into order of B.
So how you can say that order of A divides order of AB? How? I will give the argument.
If order of A doesn't divide of order of AB,
Yes.
suppose order of A is some n and order of B is some m,
Yes. Yes.
then AB raised to, sorry, order of A is n and order of AB is some other element, P or like that.
You are in right track, but first make the argument clear. You are in the right track actually, but make the argument proper. Okay, you are in the right track. Think about
Order
it.
of AB and take as order of AB as some P.
I understand. First, think about the argument, then write it down. Think about for some minutes. Okay, you are in the right track actually.
AB to the power mn, take AB to the power mn.
Yes.
That is identity.
Yes. So, AB divides M. So, order of A, B divides order of A, order of B. And also, someone say, oh, she gives some argument and which implies this order of A divides order of AB and order of B divides order of AB. So, this multiplication divides order of AB because order of A and order of B are given to be relatively different. So, this similarly give, together gives order of A. Order of B is equal to order of AB, okay? So this is solution, okay? So, yeah, so everyone understand the solution? Or any portions, any difficulty in the solution? Is the solution, is it, does everyone understand the solution? Or should I repeat the solution again? Please let me know. Whoever has doubt, please unmute yourself and ask the question. Okay. I'll wait for some minutes. Please ask your questions. And meanwhile, I let me search some problems.
Where did we use the order of A and order of B are co-prime?
Oh, okay. So, yeah. She told that order of A divides order of AB and order of B divides order of AB. Okay. Now, since order of A and order of B are co-prime, relative prime, so these together implies order of A multiplied order of AB divides order of AB. Here we have used that co-primeness. Understand? Understand? So I hope you understand. Okay. Anyways, yeah. So, okay, I hope everybody can understand this solution. If you have any doubt, please ask me. Or in the next session also, you can ask me the doubt. Okay. So one thing, do you know about cyclic groups? No, possibly it is not possible. Okay, one second. This question is not fit for the end. Yeah, okay, yeah. So consider this problem. G will be commutating. So this is the fact you need to check that any group G will be commutative if and only AB to the power n is equal to A to the power n B to the power n for three consecutive integers set. Okay. I mean, one side obvious, you need to do the reverse side. Okay. I mean, it's a quite tricky problem, but please try. Try for some minutes, then I will tell you how to solve.
So can I ask some other questions?
Ah, yes, yes, yes.
Sir, in the definition of conjugacy,
Yes.
they used one particular type of equivalence relation. So why is that?
One thing, the definition of conjugation means,
Means what is so special about U inverse GU?
yeah, from where you got suddenly this conjugation. Oh, in the group action thing you were asking, right?
Yes, yes.
Yes. So, first of all, so do you know about automorphism?
Yes.
Yeah. So you must have heard about inner automorphism, right? Inner automorphism, correct? So GX G inverse actually the inner automorphism. This is one thing, and secondly, you must have heard about Shiloh theorem, Shiloh theorem, class equation, etc. Those are actually coming from this group action. I mean, those are actually coming from this conjugation action. That's why conjugation is important actually. Okay. And you must have heard about some Cauchy theorem, which also comes from the conjugation action. And that's a conjugation action has very important corollaries. I mean, yeah. So that's why it's so special actually. Possibly at the end of this course, we shall get to know about the Silo theorem, Cauchy theorem, and all. Okay, but at the end of this course, not right now.
Sir, I know about automorphisms. I don't know about inner automorphisms. What is that?
Yeah, inner automorphism is so. For any G belongs to G, the map G goes to G, X goes to G, X, G inverse. It is known as the inner automorphism. Fixed for fixed G. Okay. So this is the inner automorphism by definition.
Okay, sir. So, given any equivalence relation, can we define like such conjugacy classes and such automorphisms? Because this is a particular type of equivalence relation we are using, right?
Yes, yes.
If we have some other equivalence relation, then we can use on that as a group action.
Sorry, I don't get you. Can you please repeat? Can you please repeat? I don't get you actually properly. Please repeat.
Uh, if we have any other equivalence relation,
Yes.
then can we use that equivalence relation as a group action?
No.
Like basically, we used this particular type of action and we call this conjugacy. If other equivalence relation if we have on that group, then some other type of inner automorphisms or
No, no. No, no. Any equivalence relation will not work. Okay, any equivalence relation that occurs from group action only for that thing it will work. It will not work from any kind of equivalent relation. Okay, there is a specialized situation. So any equivalence relation will not work here because we need the G always, right? So G will comes from the given situation only. So any equivalence relation will not work. Okay. Understand?
means I want to know what is this equivalence relation, why we came with this definition Gx G inverse. Like take this particular equivalence relation.
Yes, yes. First of all, this is not a definition. This is an automorphism, and especially known as the inner automorphism. Okay, this is the one thing. And secondly, this type of CXG inverse, this conjugacy action is important in the definition and in the theorems related to Shiloh and the class equation. Okay, that's why we have considered this example. Okay, for this time being, that's what we only can say. But at this around this end of the course, we'll get to know about the Shiloh theorem, class equation. There we'll actually see how this conjugation action gives those things as a corollary. Okay.
Okay, thank you, sir.
What about this problem? That is, G is a commutative if and only if AB to the power n is equal to A to the power B to the power for any consecutive n. Anybody has solved this? So basically, this problem is quite tricky. Okay. So let me solve it. So since it is given that, sorry, ab to the power n is equal to a to the power n, b to the power n is given. Okay. And for three consecutive integers, so we're assuming a b n plus 1 is equal to a plus 1 b plus 1 and a b to the power n plus 2, a to the power n plus 2, b to the power n plus 2. Okay. False equation 1, equation 2, equation 3. Now this equation 1 gives, sorry, equation 2 gives ab to the power n dot ab is equal to a to the power n plus 1, b to the power n plus 1, right? And this thing can be written as a to the power n, b to the power n, ab is equal to a to the power n plus 1, b to the power n plus 1. Okay. So this implies what? B to the power na is equal to a b to the power n. It's a direct calculation and cancellation. It's this thing. Okay. So this is equation 4. Now consider this equation 3. Consider this equation. Okay. This gives what? This gives ab to the power n plus 1 into ab is equal to a to the power n plus 2, b to the power n plus 2, right? This gives what by equation 2, a to the power n plus 1, b to the power n plus 1, ab, a to the power n plus 2, b to the power n plus 2, right? So this gives what? This gives b to the power n plus 1a is equal to a b to the power n plus 1, right? Now this implies what? B into b to the power n a is equal to, can be written as a b to the power n b. Okay. Now it is known that b to the power n is equal to a b to the power n. That's why we are writing this as this. So this implies what? This implies b a. Now we are multiplying another b on the right and left side. Bn plus 1 is equal to a bn plus 2. Okay. This gives what? ba bn plus 1 is equal to a b bn plus 1, and this gives ab is equal to bn. So says that it is commutable. I mean, yeah, that's so. I mean, that's what it is. It's a very tricky problem. Yeah. Basically, there is nothing to do. You need to just 1 second. I'll be back after 2 3 minutes. Hello. Yes, Amazon. Yeah. Sure.
So before that, should be hello. The existence of such n, we have to show that three consecutive numbers has to be there. Some initial case or something. Hello.
Yes, 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 yes. Please tell me. Sorry, please tell me.
So, do we need to show that there exist such integers? First of all, the existence of such n.
No, it is given that G is commutative if and only if these three holds. Suppose we are assuming that AB to the power n is equal to A to the power n, B to the power n for three consecutive integers, then we need to show that G is commutative. That's it. And we are doing the reverse direction, so obviously we are assuming existence of three such integers, right?
What if there doesn't exist?
Sorry?
What if there doesn't exist such integers?
I mean, it is not our business, because I mean it is given that suppose these three consecutive integers exist, then G will be commutative. That's it. We are assuming the existence of such thing. Okay. And the thing is, observe that it is a if and only if statement, right? It's an if and only if statement. So if this such a thing will not exist, then G is not commutative. Otherwise, it has to hold, right?
Okay, or in other way, when we say G is commutative, then we need to show that AB to the power n is equal to like A to the power n times B to the power n.
Yes.
So then we need to show that such three consecutive number exist first of all.
Yes, right.
No,
Yes. No, I mean, when G is commutative, then it is obviously true, right? Correct?
Obvious is only AB to the power n is A to the power n times B to the power n. But for three consecutive integers n, that statement we need to show the existence of three.
The thing is, whenever G is commutative, then for any integer small n, AB to the power n is equal to A to the power n and B to the power n for any integer n, right? Then obviously for any three consecutive integer n, it will also hold.
Okay. I'm sorry, guys. Got it.
Understand? Understand? So okay, so consider another problem. G is a group contains elements A and B such that order of A is equal to 4, order of B equal to 2, A cube B is equal to BA. Then find order of AB. G is a group, and in the group there are two elements A and B with order of A is equal to 4 and order of B is equal to 2. Okay. And the relation is A cube B is equal to BA. Okay, now we need to find that order of AB. Okay, it's a simple problem. Do the calculation test. Try it for some minutes.
Is it 2 or 4?
Right, correct. you are right. It is 2, right?
It seems like the same diidal group, right? Order it.
Yes, it's a diagonal. You are right. Correct. So, do you know about subgroups?
Yes.
So, can you tell what is the if and all if criteria of subgroup? I mean, what is the criteria of subgroup? Anybody, please?
It's a subset of the group and it has the same group operation.
Yes, that is the definition. I understand. What is the criteria? What is the criteria?
You mean equivalent conditions?
Yes, right.
So there is one. If A and B belongs to the group, then H is a subgroup of G if and only if A, B inverse belongs to H.
Good. And also, do you know about the center of a group?
Yes,
Okay.
all elements which commute.
Yes, yes, right. So, answer this problem. Find all subgroups of Z. I mean, so answer will be all possible subgroups are basically in Z. Okay. That is n, 2n, 3n dot 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 minus 2n minus 3n dot dot dot. Okay. So now how to check that actually, or how to prove it? That is it. Think about it.
If any subgroup is of this form is a like any set of this form is a subgroup.
Yes, yes, it is the NZ.
Yes. And if there is any other subset, then by using the well ordering principle, we can choose the least element,
Yes.
and it has to be of this form, right?
I mean, but how? How? Just, I mean, you can speak the reason also. How you can show that it has to be of the form.
So can we go by contradiction?
It's better to go directly because you have already said about the using the well-ordered principle, right? So directly from that you can show this. Just design the proper argument. Think about it. Take your time.
So first consider the set of all possible linear combinations. The set of all, and it is non-empty.
Yes.
So by well ordering principle, there exists a minimum, or you can say the GCD is the least among them, right? The GCD of
I mean, well-ordered principle is far better to use, right? Because I mean, concept of minimality comes in the well-ordered principle, right? GCD
okay,
deals with
okay, sorry.
right. Yeah, then you have to take the minimum, right? Then
So that is my candidate.
yes, yes, but how to show that it will be exactly from NZ? That is how to check that every element of that subgroup will be a multiple of n. We're almost there. Just one step left. You need to show that any element is actually multiple of small n, right? So just use the divisibility argument, some kind of.
Okay, so Z has a division algorithm.
Yes.
So if we divide it by n, any element, and if if there exists an element which is not divisible by n,
Yes.
then that contradicts the minimality of n.
Yes. Right. Correct. Very good. Let's understand the argument. What about others? What about others? Does everybody understand the argument? Okay, I hope so. Yeah. So, do you know the by what do you mean the definition of finitely generated? Do you know by what does it mean by finitely?
So I heard.
Yes, yes, please tell.
So any element can be expressed as a finite product of the product I'm saying in the group operation. It can be written as a like if G1, G2, GR
Yes, yes,
are elements of group, then
yes, yes.
any element G can be written as uh, Gi to the power Ri and product
Yes,
of
yes.
these, and where indexing set is finite.
That this group of rationals Q is not finitely generated. So that the group of rationals Q not finitely generated.
Under the addition operation, sir. Yeah, addition
Yes,
operation.
yes, it is addition operation. Yes, obviously addition operation.
Okay.
Again. Yeah, it's addition.
So suppose it is finitely generated
Yes, yes.
and the denominators have some, suppose it's S1, S2 up to SIR.
Yes.
Then 1 by the product of SIs, like 1 by S1, S2, SN, that is my candidate. That cannot be generated by these SIs. Suppose a Q is generated by R1 by S1, R2 by S2, up to Rn by Sn, where Ri and Si are integers and Sis are non-zero. Then that 1 by S1, S2 to Sr, that cannot be written as combinations of, because if it is, then 1 is written as a
Yes, Glenn. Why suddenly stop? Well, finish the whole argument.
or we can say like if Q is generated by finitely many elements, then the primes involved in the denominator. Consider all primes which are in denominator. So those primes are finite.
Yes, right.
So now take another element 1 by P, where this P doesn't belong to that finite set, and 1 by P cannot be generated, because when we take the LCM, the denominator part will contain only those primes, nothing more, but primes are infinite. So suppose Q is R elements, and there are finitely many primes involved in the denominator of these generators.
Yes.
So, but primes are infinite. So there is a prime which is not in this set. So consider that 1 by P, that prime, that element cannot be generated, because when we take all the combinations, the denominator will contain only these primes, no more primes.
Correct. Yes, your argument. Yes, so basically your argument is like, suppose P1 by Q1 dot dot Pn by Qn generates Q. Then we are choosing some large P which is greater than P1 by Pn, and then that is then
Yes.
1 by that large P can't be generated by P1 by Q1 dot dot Pn by Qn due to the divisible argument, right? You are saying like that, correct? Yeah, right.
Yes, but any prime which is not in that set, that will work. But yes, that candidate that track the product and product of those primes, that 1 by product of that prime, that will not be generated by this.
Yes, it's very good. I mean, you have said that word correctly. Very good. Okay. Can you repeat your argument for the others too? Please repeat your argument for the others also.
Suppose Q is generated by finitely many elements. So finitely many elements are like R1 by S1, R2 by S2, up to Rn by Sn. So primes involved in SIs like S1, S2 to Sn, like S1 contains some primes, some finitely many primes, S2 contains some finitely many primes, and Sn contains some finitely many primes. Consider the set of all such primes. the primes involved in the denominator. Now, the product of all those primes, no, we don't have, that candidate also work, but primes are infinite. So there is a prime which is not in this set because this set is finite. So there exists such prime. So consider 1 by that prime p. That p 1 by p cannot be generated by these combinations. Why? Because whenever we take the combinations, the denominator part will contain only the product of these primes, nothing more. Means that new prime cannot occur. If it does, then take the cross product, then that prime has to divide the product of this denominator. But this prime doesn't belong to any of them. So by the fundamental theorem of algebra, it has to divide one of the primes, but these all are distinct primes.
Yes, your argument is right, correct, perfect. Very good. Yeah. So it states that it's a finitely generated. Also, okay, actually my pen is not working, so that's why I'm writing the next question in the chat. Okay. The chat also. Okay, so do you know about cyclic groups? Do you know about cyclic groups?
Yes.
So, show that. That any finally generated subgroup of Q is cyclic. Okay. Think about this problem. Please tell me the answer in the next live session in the next week. Okay.
The same argument, right? Means the 1 upon the product of primes involved, that is the generator.
Yes, correct. But I also want to listen answer from others too. Okay. So others, please go through the problems that we have discussed and please solve this problem. And anybody of you, I hope you please tell this solution in the next live session next week. Okay. So for today, we are stopping here.
Sir, can you explain the semi-direct product once?
Semi-direct product. Next session I will explain. Okay. Because it's a very long thing. I mean, it will take 1 hour itself semi-direct product. That's why. Okay. So in the next class we will explain. Okay. Okay. So I'm stopping here, and if you have any doubt, any questions, you can ask me in the next live session. Okay, so I'm leaving the call.
Okay, sir.